Have you ever wondered how machine learning models handle predictions that involve distinct, countable events, rather than continuous values? It is like predicting a specific number of occurrences or a clear category. Understanding this is key to building robust and insightful models. Discrete probability distributions are fundamental tools in machine learning that define the likelihood of each possible outcome for a random variable that can only take on specific, separate values. Think of them as the mathematical blueprint for predicting countable results, making them indispensable for classification tasks and event counting. The core mechanism behind these distributions lies in their ability to assign a probability to each individual separate outcome. For instance, the Bernoulli distribution models a single trial with two possible outcomes, like success or failure, giving us the probability of each. Building on this, the binomial distribution extends the Bernoulli to a fixed number of independent trials, allowing us to predict the probability of getting a certain number of successes. Then, the Poisson distribution helps us model the number of times an event occurs within a fixed interval of time or space, assuming these events happen with a known average rate independently of the time since the last event. These distributions are crucial because they mathematically capture the inherent uncertainty in discrete processes. Machine learning models leverage these distributions in various ways. For classification, especially with two classes, the Bernoulli distribution often forms the basis of the final output layer, interpreting model scores as probabilities of belonging to one class or another. Similarly, when models need to predict counts, such as the number of errors or network traffic spikes, Poisson regression is a common technique, directly employing the Poisson distribution to model these non-negative integer outcomes. They allow a model to not just make a prediction, but to also quantify the confidence or uncertainty around that prediction. A deeper understanding of discrete distributions allows you to go beyond just using them as black boxes. For example, in a classification context, applying maximum likelihood estimation means finding the model parameters that make the observed data most probable under a chosen discrete distribution. This method implicitly uses the properties of these distributions to optimize model performance. Moreover, incorporating prior knowledge through Bayesian methods often involves specifying these distributions as priors, which greatly influences how the model learns from data. Ultimately, grasping discrete probability distributions empowers you to select appropriate models for different types of problems, interpret model outputs with greater nuance, and build machine learning solutions that are both more accurate and transparent. They are the backbone for understanding and predicting a vast array of real-world phenomena with countable characteristics, transforming raw data into meaningful, probabilistic insights.